To understand the complex field of thermodynamics, we must first clear up a common, persistent misunderstanding. Many people assume that heat and temperature are identical, but they are actually quite different concepts. Let us begin by defining temperature, which is a measurement of the average kinetic energy within. Everything in our physical world is composed of tiny atoms that are constantly in some motion. In a cold object like an ice cube, these atoms are moving very slowly and shivering. Because their kinetic energy is quite low, the overall temperature of the object remains very low. Conversely, in a hot object like boiling water, those same atoms are dancing with violent intensity. They vibrate rapidly and ricochet off each other at high speeds within the liquid's internal structure. That high level of kinetic energy translates directly into a high temperature for the boiling water. Now, let us turn our attention to heat, which is a distinct and separate physical process. Heat is defined as the actual transfer of thermal energy from one object to another object. Thermal energy follows a strict, unbroken law of nature that governs how all matter behaves today. It always flows from the hotter object with fast-moving particles to the colder, slower-moving object. Imagine holding a cold ice cube in your hand on a warm and sunny summer afternoon. Your hand feels cold because thermal energy is actively leaving your warm skin at this moment. That energy rushes into the ice, causing the solid structure to break down and melt away. Heat never flows from cold to hot, as that would violate the fundamental laws of physics. This microscopic dance of atoms is the hidden engine behind every single temperature change we observe. When you touch a hot metal pan, you are feeling the rapid vibration of those atoms. This energy is transferred directly into your skin, which your brain interprets as a painful burn. The faster the atoms move, the more thermal energy they carry and the hotter they feel. By observing these particles, we can see why objects change state from solid to liquid form. Temperature is the state of the atoms, while heat is the energy in transit between them. This distinction is crucial for understanding how energy balances itself across different materials and environments daily. Consider a cup of coffee sitting on a table, slowly losing its heat to the air. The fast-moving atoms in the coffee collide with the slower air molecules surrounding the ceramic mug. Energy is transferred outward until the coffee and the room reach a state of thermal equilibrium. This process continues until the kinetic energy of the particles is evenly distributed throughout the space. Nature always seeks this balance, driving heat to move until no temperature gradient remains between objects. The microscopic world is a chaotic, bustling place where atoms constantly exchange energy through these collisions. Every time you adjust your thermostat, you are manipulating this flow of energy on a scale. You are essentially controlling how fast atoms move and how they interact with their immediate surroundings. This is the essence of thermodynamics, the study of energy, work, and the heat of matter. It explains why the sun warms the earth and why your refrigerator keeps food cold inside. Without this constant flow of thermal energy, our world would be a static, lifeless, frozen place. Instead, we live in a dynamic universe where energy is always in a state of flux. We can measure temperature with a thermometer, but heat is the invisible movement of the energy. It is the kinetic pulse of the universe beating through every solid, liquid, and gas form. By mastering these definitions, we gain a deeper appreciation for the physics governing our daily lives. The next time you feel a warm breeze, remember the atoms dancing in the summer air. They are transferring their kinetic energy to your skin, making you feel the heat of summer. It is a beautiful, invisible process that connects every object in the universe through thermal energy. We must remember that temperature is just a snapshot of the average energy of the particles. Heat is the journey that energy takes as it moves from one place to another place. This journey is governed by the laws of thermodynamics, which are as reliable as gravity itself. Whether it is a cup of tea or a giant star, the rules remain exactly the same. Fast atoms always share their energy with slow atoms until they reach a common, stable state. This is the fundamental principle that allows us to cook our food and heat our homes. It is the reason why we wear coats in winter to trap our own body heat. We are essentially trying to slow down the transfer of energy away from our warm bodies. Insulation works by preventing the rapid movement of heat from our skin to the cold air. It keeps the kinetic energy close to us, maintaining a comfortable temperature for our survival today. Understanding this microscopic dance helps us design better technology and live more efficiently every single day. So, keep these concepts in mind as we explore how heat travels through different physical mediums. We will soon see how conduction, convection, and radiation utilize this energy in very different ways. Each method relies on the same atomic principles we have just discussed in this brief introduction. The universe is a vast laboratory of thermal energy, and we are just beginning to understand. Stay curious as we dive deeper into the mechanics of how heat moves across the world. The dance of the atoms is only the beginning of our journey into the thermal universe. Let us continue our exploration into the fascinating and invisible world of heat and thermal energy. Having explored the fundamental nature of heat, we now see how these three pillars regulate our world. Conduction explains why we use wooden handles on metal pans to prevent burning our eager hands. Meanwhile, convection currents explain everything from the swirling motion of boiling soup in a pot to the massive, rhythmic movement of global ocean currents that help stabilize our planet's complex climate. Radiation explains the instant radiant warmth we feel from a campfire or the bright morning sun, even when we are not physically touching the source of that intense and life-giving thermal energy. Together, these three distinct processes maintain the delicate energy balance of the entire, vast, expanding universe. By mastering these concepts, we move beyond simply observing phenomena like melting ice or rising balloons. We start to see the microscopic physics driving them, hidden beneath the surface of our reality. Whether it is the vibration of atoms in a spoon or silent cosmic waves traveling through, thermodynamics serves as the ultimate engine of motion, dictating how energy moves through our daily lives. Recognizing these patterns allows us to appreciate the complex, invisible dance that keeps our world functioning. Every interaction we witness serves as a testament to the laws governing the transfer of heat. From the smallest metallic spoon to the largest star, energy is constantly shifting and changing form. This constant motion ensures that no system remains truly static for any significant length of time. We observe the world with new eyes, seeing the invisible threads connecting every single warm object. The cold air rushing into a room is just as much a part of the dance. It is a relentless, beautiful exchange that defines the very boundaries of our physical existence today. Science is truly everywhere we look, woven into the fabric of the air and the ground. We are merely spectators to a grand thermal performance that has played out for eons past. Each transfer of energy tells a story of atoms colliding, rising, or traveling across the void. Understanding this flow grants us a deeper connection to the environment that surrounds our fragile lives. The laws of thermodynamics are not just abstract equations written on a dusty, old classroom chalkboard. They are the living, breathing rules that dictate the temperature of our coffee and our climate. As we continue to observe, the complexity of the world begins to simplify into elegant patterns. Heat is the language of the universe, and we are finally beginning to learn its vocabulary. Every movement of air, every shift in temperature is a verse in this grand cosmic poem. We find comfort in knowing that even in the cold, there is a subtle, shivering energy. The dance continues, undisturbed by our observation, yet enriched by our newfound ability to perceive it. In every corner of the globe, the invisible dance of thermodynamics persists, shaping our shared future.